Good morning, everyone. Good morning, all the participants.
Uh, so good morning, everyone. So, am I audible to everyone?
Sir, yes, sir.
Hello. Okay. Okay, sir. So today we'll start the session, second day session. Okay. So today we'll start the session. Our today's speaker, Dr. Bharat Hardas Aital, sir. So it is my privilege to introduce our speaker for this session, Dr. Bharat Haridas Aital, Associate Professor at Ranabir and Chitragupta School of Infrastructure Design and Management, IIT Kharagpur. Dr. Bharat sir work lies on the dynamic interaction of urban informatics, geoinformatics, climate modeling, and spatial data science. So his research has been instrumental in shaping the how we model the urbanization, assess environmental resilience, and apply machine learning to infrastructure planning. With an impressive academic profile that includes 60 journal publications and 8 book chapters and his other two books, more than 120 conference papers and 50 technical reports. So Dr. Haridas sir contributes are more both profile and deeply impactful. His contributions are more deeply impactful contributions. His recent work on digital data observations for smart cities is helping redefining the spatial data accessibility and decision making in urban infrastructure. He has been honored with several prestigious awards, including Indian National Geospatial Award, Young Engineer Award, and Sahadri Young Ecologist Award, recognizing his leadership in integrating the geospatial intelligence with sustainable development goals. Today, so Dr. Hardas sir will share his insights on how remote sensing and machine learning are revolutionized civil engineering from intelligent land use modeling to predictive analytics of infrastructure system. So so now I will ask Haridas sir to take over the session uh, from now onwards. Sir, Bharat sir, hello sir, Bharat sir, hello, not there. Ah, sir came. He came. Hello sir,
Hold it.
hello sir. Good morning sir, Bharat sir.
Can you hear me?
Yeah, yes sir, yes sir.
Right. I'm sharing my screen. Is this visible?
Yes, sir. Visible, sir.
Okay, somehow I am not able to see it.
Sir, your screen is visible to us.
Your phone, sir, phone is on mute.
Huh.
Mode. Huh?
No, unmuted.
Am I audible now?
Yes, sir. Yes, sir.
Right, right. Very good morning to all of you. I'm Professor Bharat Haridas Aital. I'm from School of Infrastructure. Uh, I was asked to deliver or deliberate on various aspects of remote sensing applications using various well-known techniques. So I would, as per advice of Dr. Sai Priya, I would take you on some applications. I would run you through some of the applications which has been recently developed by my team and have been applied in various applications. So you will be able to knit in by the end of this particular talk that how an entire model of any city can be very clearly built. So I'll run through these details. I would skip the basic stuff as advised by uh, Dr. Sai Priya. So I would just go through some of the applications which you'll be able to understand it much better when I'm speaking. So I'll just quickly get through. These are some basics of remote sensing. So if someone is interested in understanding all these things, maybe I can send you these slides and you can look at some of these. Okay, so my basic work is basically looking at urban growth modeling, land use analysis, and such aspects. So I'll give you a brief overview of what is urbanization. Most of you know it, but my perspective of urbanization is a bit different in terms of looking at how the urban growth of cities are happening. So when you look at urbanization, I refer physical growth of urban region, which means any paved region that is there in the city. So some of the people have their own examples of if there is only built area, it becomes an urban growth. But my definition of urban growth is anything that is paved. So if there is some soil being covered, then it is called the urban growth or urbanization of a particular region. So there have been several issues or several aspects through which urban growth has happened. It may be economic transactions, it may be government that has been looking at it, or knowledge exchange that has happened, or transport trade. So there are a lot of influencing factors that have come through in terms of how the growth has happened. So now what basically happens when such growth happens in a particular region or a nodal area? There'll be a lot of people coming from other regions to that particular region. So basically in countries like India, we have seen that most of the urban growth is happening because of people migrating from other regions to a particular region. For example, if you take a look at Karnataka. So the nodal region there becomes Bangalore. So everyone have, I mean, most of them have been, I mean, traveling or migrating out from rural areas or other regions of the country to Bangalore and settling down there. So this is one of the major factors in India which has been contributing to the urban. Now, having said that, yes, we have also increased in population. So the level of urbanization has also increased over all cities across India. So the tier one cities are the most are the cities which have affected the most in terms of urban growth and its amenities. So now we have to understand how this urban growth is happening. So normally, when you look at urbanization, there are two forms. One is planned.
Sir, excuse me, sir. I'm sorry to disturb.
Yeah.
Just for a minute. Actually, there is some technical issue, and a lot of our participants can't able to actually see it. For at least 3-4 minutes, we need to just hold on, and
Sure.
we can restart the session, sir. We are very sorry for this.
Yeah, please. Okay.
We will inform you again, sir. And all the participants are requested.
One is because they are dispersed development outskirts of the city. Most of this urban sprawl, first you have, let's say, let me give an example. If you are traveling from a city center to some other city or some other small town, in between a highway that connects, there will be a small tea shop at first. Maybe after 5 years, that tea shop will become a small region where there will be a pocket of 10 houses, and similarly that will grow and that will become a smaller town, and then that becomes a city. So like these growth, they don't have basic infrastructure and basic amenities that are needed for that to become a city or a town. So these infrastructure, when these are not there, these are the regions which suffer the most. So most of the developments that are not regulated have these issues in today's context. So what they basically have is they impact the environment, they impact the human health, and finally, when we are seeing it in a longer run, these create issues with land use and land cover change, and that impacts our health, our environment, our air, and everything that is associated with humans per se. So when we look at this, there are various ways of people putting it, but USHUD, which is the governing body of urban development, which looks at such aspects, they put it in three different forms. One is low density. I gave an example of tea shop. That's a very low density development. Certain development happens across the stretch of that highway. Then it becomes a ribbon development. It goes through like a ribbon. There are certain development which are very spontaneous. Within few years, you can find out that entire region is gone. It is completely urbanized. Then such types of development are called as leapfrog. So like this, there are different characteristics of how the urban growth happens. And in today's world, most all of these are very much found in every nook and corner of the entire globe. So we have to address this. So when we are addressing this, the first thing that actually came up is looking at it as a smart city. So when we say smart city, so this is more of looking connecting each and every dot, which means we need all smart solutions in terms of looking at various connectivity, various features, and how they are actually connected. So the first thing that we can see in a smart city, looking at a smart city, is an ICT. So if there is an ICT, then probably your entire data that is coming out from a smart city can be actually visualized, virtualized, and it can be looked at in an efficient way. Similarly, in today's world, we look at artificial intelligence as one of the major aspect of how these smart cities are growing. I'll show you some of the examples of how planning and optimization can be done in terms of utilizing this artificial intelligence. And similarly, probably you have looked at Internet of Things, where automation in buildings, homes, offices are looking at wireless networks, which are more in today's world as more connected and learning about us, learning our details, learning about how we are looking at internet, how we are looking at data, how we are trying to combine data or consider data for our daily life. So this becomes another important pillar in terms of looking at smart cities. And then there is sensors. So today in today's aspect, even where probably where you are sitting, there may be many of these centers or sensors that have been really put in order to look at how the smart cities are growing. And finally, there is technology which actually is going to monitor all of these, and yeah, this is going to connect everyone through every aspect of trying to develop and map anywhere on the globe. So basically, geospatial technology is to tell you that where you are and what you are. So it is going to connect all the aspects that I spoke about in the first in the smart city slide to every other aspect on the ground. So this is like the one that is holding up most of the technologies. So when we are speaking about geospatial technology, why this has to be understood is because This is one of those technologies which can look at dynamic part of the Earth's surface. You can sit anywhere, and when that dynamicity is there in any process, you can easily capture it without and also capture the temporal complexity, which is extremely important. Now, when you are looking at this, you are trying to map certain thing or trying to extract features from certain regions or trying to understand your networks well. So you need to have an unbiased identification, and remote sensing gives you these unbiased identification. So having said this, having said the qualities that we need in looking at remote sensing per se, or looking at different features of the Earth's surface, we need something called, rather than a smart city, it must be a smart regional development. So when I say smart regional development, uh, we have to have something like an ecologically friendly, technologically integrated, and a meticulously planned cities. Today, cities have technology, but the thing is that we don't have the cities that are ecologically friendly and meticulously planned. So if we use this information technology, if you combine all of this information technology which I spoke and put it in a place and make it ecologically resilient and meticulously planned, probably we are going to survive for next 200, 300 years. Otherwise, there may be really many cities who is in the verge of either, completely vanishing from the resources that they basically need. So yeah, this I have spoken about all these things. I would just skip. I'll just look at geospatial technologies, which are future cities. Now, when you are looking at future cities, when you're looking at geospatial technology per se, the first very big aspect that is actually coming up is terrain visualization. How do you visualize a terrain? How do you extract features from the terrain, and how do you allow them to visualize in different aspects? The next concept that people are looking now is virtual reality. How in virtual reality you are trying to build up the entire city, and how are you trying to maintain every infrastructure across the city frame? Then if you have seen Google Maps and Google 3ds or Microsoft 3ds, now the 3D city models have become extremely important in terms of planning and in terms of provision of basic amenities. So, and yeah, digital roads. So I'll give you examples of each of these on how you use geospatial data in order to look at all of these aspects. But these are the things that are really evolving quickly, and probably next 5 years you will be able to see a lot of information about this. And yeah, so again, geospatial data is also bringing in a lot of road safety data, which is the biggest concern in terms of today's urban growth. And the safety and security becomes a very the topmost or the umbrella part of any technology that comes up in terms of looking at how the data is being utilized. So yeah, so let me give you one case study, and then I'll give you some of applications that can be utilized in terms of geospatial data. Let me take one city. I hope many of you know, and many of you have visited Bangalore. Bangalore, if you look at today's Bangalore, it has outgrown itself from what it used to be. It was established by a ruler of a small region whose name was Kempegowda in 1537. So it was only 2 square kilometers, exactly 2 square kilometers. So a very small area. Now then it was expanded by Tipu Sultan and Hyder Ali to 7.9 square kilometer. Even that is extremely small in today's context. And then Britishers made it a city which is 69 square kilometer. And finally it became BDA, or Bangalore Development Authority, in 1963 with 112 square kilometer, and gradually started increasing. And by 2006, it was increased to 696 square kilometer. Then in 2011, it was further extended to 741, and now it is being extended to 1,264. Being proposed to be extended to 1,264 square kilometer. Now, when you see the growth of a city, when you look at Bangalore, Bangalore had a lot of lakes. So the biggest pipeline was when you are looking at this is wherever there is lake next to that is a settlement. So that's how Bangalore grew as a city. Now, if the growth of the city has happened or the boundary of the city has increased from 2 square kilometers to 741 square kilometers, and today it has been proposed to 1,202 square kilometers, you can see that how the population also grew. This was 1951, hardly any population in Bangalore. Bangalore was called the Green City, or it used to be a retirement city for many of them. People from Hyderabad, people from Andhra Pradesh or Telangana, today's Telangana, rest of while entire Andhra Pradesh, and lot of people from North India used to come down as a retirement city in Bangalore. Bangalore was such beautiful green cold climate because it sits on a hill. So Bangalore is completely a hill. So the center point is where Institute of Science is located. So that's the topmost point, and from that it is completely a hill in all the directions. So when you see that, it is you can see that in 1951 there was hardly anything, and 1961 there was some growth in central parts of the city, but yet it was quite green. And 71 is where you can see some accumulation in the center part of the city where the population density started increasing. Some of the very well-known the government industries were set up in this particular region. Then 1981, you see growth in terms of provision of workforce to that industrial growth, and we had a lot of education institutes coming up in this particular time. And similarly, 1991 was the major change where you can see the Pinia Industrial Estate and the Yeshwanthpur Industrial Estate was actually put up, and that grew in a very large scale. And this drove the entire development of this particular region. So if you see the same thing in 2001, we see that IT revolution happening, and wherever the IT revolution happened, you can see that there was a growth, especially in the outskirts of the city, which is closer to Kormangala and that region, Electronic City and that region. So that grew in a large scale, and finally, when you see in 2011, you can see the densification in the center. So it is crossing the threshold that it can carry. And now today, if you see the city is quite, grown in terms of population density, and you won't even find spaces in terms of how the growth can happen in future years. And similarly, just to give you how the urban growth happened. So if you see, this is in 1992 when the industrial estates. I have just given some of the names of well-known areas so that you understand if you have visited Bangalore and if you have stayed in Bangalore, you will be able to connect this. So in 1999, this was the growth, and 2002, Indranagar, Kormangala, BTM layout. These are the regions where your IT industries came up, and this started growing even more. So this is in 2006, 2010. So just another visualization of how it grew. This is in 2008, 2010, 14, 16, 2020. So this is how the growth pattern of that particular city. So here we used a very simple machine learning technique, which is called maximum likelihood, and we also used a SVM classifier in here to understand how the growth happened in Bangalore. So we also published this particular thing in current science, where it was also a discussion in the parliament, which actually was one of those triggering factors in order to see how the city growth rates are to be controlled. So if the new bylaws are being thought about, is because of this particular paper. You would have, if you are sitting back, you would have seen these pictures many number of times flashed either in your news channels or in on your probably in the newspaper. Yeah, so we did write this article. So you can see the transition here. I have shown this here so that you can understand. Bangalore sits on a hill and a valley. Here, this is the topmost point. So this is three different valleys in Bangalore. The waterfall, whatever the waterfall falls here is going to drain it out. So if all of these are lakes, interconnected lakes of Bangalore, so now we are choking each and every connectivity in these lakes. And when you see those lakes being disconnected and there is no water flowing out, then probably you will have urban floods, the flash floods that are going to be there. And you have been seeing that very frequently that these floods have been reoccurring and occurring and occurring. So this has been the same situation across various cities across India. So these are different cities across India where you can see how the urban growth has happened over a period of time. Now, when we did this, the first question that was asked to us was, okay, so if the urban growth has been happening like this, can you tell us uh, in next 10, 15 years, what is the kind of growth that may happen in these regions? And where would be the growth? We have to tell them very exactly, pinpointedly that these are the places that will grow. And I'm sure that what are the growth models we have proposed, and if you see those results and go to those points, and today the growth has happened in those poles, but authorities have never addressed such issues yet. So when we look at different growth models, there are huge number of growth models across people have looked at. But the very well known growth model is using a celio-automata based growth model. When I say celio-automata, it is on the neighborhood principles. When a cell is being formed, it looks at its neighborhood. If there is a cell that has a neighborhood which is completely urban, so that cell transforms itself into an urban area. But if there is a cell that is completely surrounded by vegetation, so that cell may transform over a period of time into a vegetation. So it is based on a certain amount of rules that we feed in as an intelligent part of optimization in terms of these models. So one of the models that we chose was looking at sleuth. Now, when we look at sleuth was actually developed by Clark et al., who actually developed this as a part of just looking at an urban landscape. But when the sleuth gave wonderful results, this was extended to looking at a modeling part of how the land use change is happening. So when you look at results of this sleuth, this gave something wonderful in terms of where the exact growth schedules are happening. For example, in Bangalore, if you see, it clearly stated that very closer to highways are the regions which are going to grow. So if you go and if you probably travel today, either from Chennai, either from Hyderabad or Mumbai, you will be able to see that all of these highways, the growth has rampantly increased, and almost these areas have thresholded in terms of urban growth. So probably if you travel from Hosur to Bangalore, you will appreciate that this particular model was to the point of saying where the growth is going to happen. But the thing is that when you are going to look at different big cities across India, these models have a lot of consumption of time, space, and also computational efficiency. So now you have to look at the computational efficiency, look at time, look at this thing, because on a real time, if you have to tell them, so you have to look at how it's actually happening. So what we first introduced was looking at particle swarm optimization. So probably you know how the swarms of these birds happen. So most of the birds fly out from one region to the other region through swarms. So these swarms, when you really understand these things, each particle or each bird has a best fit in that swarm, which means a best fit region. Only in that region it actually transcends and moves across. So when you look at this PSO as a bird flock mechanism, each search phase or looking at different growth patterns of the urban city is through your bird flying space. And every bird is treated as a particle and has its own solution in terms of how it grows. So if you look at the iteration 0 to iteration n, so you can see there are different birds moving out in a different direction. So you are going to provide a different solutions for each of these birds, which means entire image of your remote sensing data that you consider for a city, you will have a specific point of view in terms of how these are transforming. When you look at sleuth per se, it's only looks at neighborhood, so it is not looking at the entire global or the entire part of the image. So now we are going to look at more locally in terms of how this iterations happen. So we introduce this in terms of agent-based model, which means agent is going to actually create the new laws in terms of how the growth patterns are there. We learn from different previous nature. For example, we input the data from 1990s to 2011, how the growth has happened, where the growth has happened, growth factors, different growth agents that are influencing. For example, I gave an example of a tea shop. That is one of the growth agents, but there may be several agents like that. Similarly, we looked at different agents that are there. Almost 16 different agents were prioritized in terms of uh, how the efficiency in urban growth is there, and with that agents we could model how the growth used to happen. So now with that we again came up with this particular model, which actually was more in terms of efficiency. It increased, though it did not increase spatial validity, which means whatever the spatial modality in terms of sleuth was there, the same, almost the same values were seen. But if you see here, the percentage urban, which was 0.9950 in sleuth, now was 0.999992. So that was a small, very small difference. But what the major thing that you see is the computation time. So sleuth used to train itself for 7 hours, which was drastically reduced to 4 hours. With this, similarly, we went to different models in order to look at it. Today, I will not be able to give you all of those models, but probably you can look at our publications to look at different models per se. So now when you look at most of the cities, you cannot look it at as a single city or standalone city. Now the growth is more of a ribbon. So if you see this ribbon kind of growth across the globe, so you can find out all of these regions that are there, and most of the regions are across India. So then we started also looking at, okay, if there is a ribbon growth, then probably we have to look at the entire ribbon area. So we started looking at this particular corridor, which is essentially one of the biggest corridors, starting from Mangalore and ending at Chennai, which is crossing Bangalore and many other well-known places. So, and the other corridor that we looked at is from Mumbai. So let me show you. See, this is how the transformation of land use happened, and we predicted that in 2029, this corridor is going to be saturated in, especially in places where Hassan, Vellore, Kanchipuram, and Hosur are located. And probably you can see these have become today the most driven regions where you cannot find a lot of open spaces. And these also have become black spots in terms of where accidents are happening very regularly. So there is some correlation in terms of how this growth is happening eccentrically, and how the kind of change that is happening. So when you see this, the other part of this is how the climate change is happening. So we also looked at land surface temperature as one of those indicators indirectly affecting the climate of a city, or one of those indicators which tells us how the cities are growing. So we went back to the literatures, looked at different mechanisms to extract data across the globe. People had used various other methods like single channel method. This only utilizes data from one set of thermal image, whereas there is a split window method where it needs two thermal images in order to extract the data. Especially if you take up Landsat data, you from the Landsat 7 series, probably you have two bands of data, whereas the previous series you have a single band data. So other than that, if you are not completely dependent on satellite data, and if you have some of those data in situ, so probably you can look at radiative transfer equations and temperature sensitivity estimation. So that also we looked at it. I'll quickly run through these things. So this is for Kolkata. If you see, this is about single channel and radiative transfer equations. If you see how the central Kolkata is where you are actually transitioning in terms of the temperature growth. And this is the region where exactly the urban area has been spurted out. So this is not the Kolkata city per se, this is the entire region of Kolkata Metropolitan Development Authority. Kolkata city is only this part of the region, very small part of this region. So the central part where the red area can be found. Now, this is for split window. So all of these are actually giving us that the growth is happening, and because of which there is increased temperature. And when you see it, when you profile it across the region, probably you will be able to say that vegetation and water body is actually sinking it to a very large extent. So when you go to Kolkata, there are a lot of local water bodies, and this local water bodies and because of some vegetation that is already present there, Kolkata being very old city in terms of development, you can see the temperature decrease in wherever there is the urban growth is happening because of vegetation and water. So though the urban areas have about 35, 36 degrees as temperature, where vegetation, immediate surrounding has certain vegetation and water, which actually is controlling that particular temperature profile in that particular region. So similarly, when this was presented, there was some questions. Okay, can you give us indicators to say where exactly the growth change of growth is happening? So we looked at indicators. They also asked us whether we can try to establish a relationship, and when we established it, we could easily find out that urban area, where the urban area is there, that is the region where the temperature is going to increase or heat up. It is for various reasons. It may be for how the design for building is done, or it is also because of the entire region being paved and there is no emissivity in terms of absorption or emission of these heat in terms of soil. So yeah, this is another profile graph. So, having said this, there was another question that was raised, that if this is so, can you tell us if there are, in a city itself or in a particular small region itself, is there a temperature change? And what is this temperature change being dictated about? So, we went into looking at 3D surfaces, and when we looked at 3D surfaces, you could see this. This is Tikiapara. So, this region which is there is completely urbanized, whereas this is the region which is very close to the river body, and if you can see that the temperature is much lesser in this particular region, whereas this is far away from the river, so you could see much higher temperature. Similarly, very well known Park Street, so it too has very high temperature at a particular locations where mostly glass facades are there, or the big buildings with glass facades are there. So it is absorbing a lot of heat. And this is Bidan Nagar. This was considered to be a more planned place, but because of its growth over a period of time, it's also it is also experiencing heavy heat in terms of higher temperature and heat capacity. We also developed a neural network chain in terms of how the growth of this region is related to how the temperature grows, which means that we had various layers. For example, LST, which I showed you over a few slides, are some of its inputs. Then we had certain input layers like urban UI. Urban index is one of the input layers. Similarly, we have land cover indexes as input. So these, when you see land cover indexes, each of these index are representing different feature on the Earth's surface. So each of these are going to give us certain inputs in terms of how the temperature is going to rise. So this, using this, we try to develop this particular model. and we could see the kind of growth that will happen or kind of temperature that will rise over a period of time. And we could establish that with field evidences and correlating it to the data that we have already received. So these are some examples of that aspect. Now, having said this, this is on a I mean, when you look at this is on an entire city scale. Now we had to go into a per building basis in order to understand each of these aspects, the growth aspect, the way it is growing, the materials that are being used, and how these are being, looked at in terms of growth patterns. So we looked at building footprint. For example, when you see, you have two concepts in terms of looking at photogrammetry. So you have DSM and DTM. DTM is more of a terrain model, which means it gives you the terrain of that particular region. But when you look at the digital surface model, it is going to give what is there on the surface. If it's a building, it is going to give a building. If it's a tree, it is going to give a shape of a tree, and so on. So you are able to understand what kind of feature is there on the ground. So using these aspects, we could generate the height maps. We use some very well known satellite data. One is a triple sat data. This is an 80 centimeter data, which means one pixel of this data is 80 centimeter by 80 centimeter, which means even the room that you may be sitting now can be represented in maybe 10-12 pixels if it is a medium sized room. So this is a list 4 of Kolkata. So we use different kinds of data so that the algorithm will be able to understand it much better. So this is a Cartosat data. So we started retrieving building footprints across the region. So we use a simple UNet architecture. UNet is one of the very well known deep learning techniques in terms of how we see the spatial data being absorbed. So since it has a U shape where the convolution and deconvolution happens, so then it's called a UNet. I'll show you that structure about in few slides. So then we also went on the ground. We looked at ground aspects and we mapped each and every building on the ground wherever we wanted to take samples. Along with that, we also notified using a photogrammetric camera, and that was done in all of the cities that we considered. And you can see this building heights that have been measured of matching whatever the ground truth that we have collected. So yeah, this is example of an elevation data, and this is extracted building footprint. Now this is automized, so I don't need to really put in my effort in order to get this information. So you feed in satellite data, it extracts the building footprints with developed algorithm, and it is going to extract data. So now the first thing that we looked at is using a CNN architecture at first. Then we looked at how we can use a UNet architecture. Because of its shape being U, it's called a UNet. So okay, if I may need a special class in terms of explaining how the UNet works, but we modified this particular UNet. We added a edge block in here, so that we can extract much more detailed information in terms of how the growth is happening. So yeah, these are some examples of model training. These are the model outputs. So if you see this model accuracy and model loss, it is model accuracy is increasing over a period of time when the training is happening, and when the model loss is decreasing when actually we are training it more in terms of how these data are being looked at. So these are some of the visual analysis of results. This is for different models. And this is for Salt Lake. This is on IRS data. So once we have done this, we also transformed it using different methods, and finally, finally looking at this, we could develop the both horizontal profile and vertical profile of a building. So this is how the final 3D view would actually look like. So this is already online. So some of these data can be easily accessed at this point of time. Now, having now said this, the main question was, can we classify this particular data? Which means whether the data can be looked at as a commercial building versus a residential building versus commercial versus commercial and residential and so on. Such categories can be done. That was one of the questions that was asked. So we looked at how we do it. So we then introduced another module which is called another deep learning technique, which is YOLO, and we then combined it with SAM segment anything model. So both of these model put together was proposed in order to look at the segmentation. I'll just show you the results instead of this. So if you see, this is the zone-wise classified map where there is where there's residential versus non-residential versus mixed residential. So now what we are trying to do is that once we have understood this, now we have to attribute data, we have to add attribute data to it. I cannot just give zone wise, so I have to give building wise. So now we have started looking at how to do a building wise data. Though we have building polygons that we have generated, I'll show you also one of the examples later how the building polygons have been generated. And with that generation, we have also started looking at this data in terms of how we can attach information very clearly. Similarly, once we have done building, then the next part is looking at roads. So we took the same unit model and introduced an edge block to it. So that, for example, when you see here, there is a building in the images on the top. That building has a certain amount of cloud. So this shadow. So if you have such shadow, this has to be removed in order to get exact features. In Indian context, you have trees, you have shadows, you have uneven surfaces. So all of these has to be normalized in order to extract features from an image. So we introduced some method called SCLAHE, which reduced or improved the intensity of that particular image. And if you see the image below, you can see that shadow has been normalized and you can at least see some part of road structure in it. So with this road structure, we introduced the edge block. This edge block is where we could improve the structure of a road. If you see the structure below, you can see that the road structure has improved greatly. I'll show you one example here. So unit that we proposed, you can see that though it was actually leaving out many roads because of some of these aspects, we could improve it with the road structures. You can see in the proposed model, wherever there was some of those road structures missing, you could see that road structures have been improved in this particular model. It can be seen in the first top image of a screen. If you look at specifically here, so you could see that the region is very well done now. Okay. So these are some results of this proposed model. Probably you can look at some of this data which we have put it on the web in GitHub so that you understand. And this particular model is also available on GitHub, though, so that you can download it and utilize. And people said, okay, you're using on a benchmark data set. Why don't you do it on an Indian data set? So we did a drone survey for the region's outskirts of Bangalore, and we could get a lot of data in terms of road. So we could extract that and exactly show that how better is our proposed model in terms of looking at it. And yeah, these are some of those statistics. Our model was much better in terms of number of parameters that are used, which means it at the most lowest parameters in usage, and because of which the time that probably we could utilize is much lesser. And similarly, we developed routines. Now, as I said, you have a data. Okay, that data is going to sit on certain. When you do that data, it is going to be on your framework, but it is not going to have certain information related to that particular region. It doesn't have certain geospatial information which is necessary for anyone to use. If I'm generating data, the public should be able to utilize it for various reasons. We can even develop our own set of indigenous surface reference maps in order to do our analysis much better. So we started developing this particular feature here where we have a sample referenced image, we have our own algorithm that is already built. So once we have done it, the output, the segmented output that we get, we then add geospatial information into it. That geospatial information along with the attribute information, which says the size of a road, what is the approach road, name of a road, etc., were added to it. And then this was in a fly uh, been given as a vector data. Vector data is point, line, and polygon. So now this polygon or a line can be utilized in any of your mobile phones also in order to see where the road is, how the road is today in today's context, and what's the size of a road, how if the road is of good built or not. So all of these features can be easily seen in this proposed framework. So this is how it worked, and this is a sample code where we develop the geodata frame in order to develop this particular task. So yeah, we looked at various data sets. So whether it is residential campus, whether it is Indian data, etc. Now, having said this, the next thing that people asked for was um, when you are driving, you know that okay, roads are in this particular aspect. Now the thing is that people have been trying to develop autonomous vehicles. So how do we actually see this as one of those aspects? So uh, when you look at most of these autonomous data sets that are available, so most of these do not have a proper lane segmentation label. So it is very difficult for you to develop any kind of algorithm in order to see it or understand how the features are. So what we did is we took a help of IIIT Hyderabad. With help of them, we could survey that entire region around Hyderabad in order to capture road data. So with that road data, we started looking at lane segmentation, which means any data that is coming out of such analysis, if there is a vehicle that is collecting data for all throughout the day, or if there is some sensor that is collecting data all throughout the day, it has to automatically segment those lines into LHS and RHS so that we can have proper marking schedules and making uh, driving much easier. So we started looking at it. See, this is one of those campus data sets where this data was considered, the label was created, and with that we could predict the center line of that particular road. Okay, what is the exact center line? So based on that center line data, we can say whether you have to drive on the left or it is on the opposite way that you are actually driving. So uh, with this uh, with this way, since we had this kind of information or this thing, then was okay, if we have road, then we have to also look at trip, which means how the trips are being organized and looking at traffic density and traffic volume and trying to improve the conditions in terms of the driving aspects was another cause. So what we did is we started surveying with video data. So if you see this, there are different data being captured that vehicles are driving and people are moving. So we have motorized vehicles, we have non-motorized pedestrians also. Both non-motorized vehicles and also pedestrians. So we looked at it in two different aspects. So then from this video, the frames were generated. Now we have a module that is targeting, which is very clear that when these frames are generated, immediately we know where the vehicle has started, where the vehicle is ending, what's the trip duration. So if that there are large number of trips, how do you actually try to have a separate trip round in order to avoid traffic density in a particular junction? So we started looking at this. First thing is looking at vehicle identification. So this vehicle identification, because we need to know where the trips are going, how long is the trip. So this becomes the first step in looking at it. So then we generated the number plate identity, so which is going to generate where actually trip has started. For example, if you look at this particular slide, region 1 out to region 1 in, which means where it is going out and where it is actually coming in. Similarly, region 2, region 3. So each of these regions have different labeling in order to see that where the vehicles are moving. So higher the number of vehicles, so which means that region has higher density. So the next step starts in terms of looking at how vehicle density versus that particular region is behaving. So then similarly, we looked at non-motorized video traffic data. So if you look at this, there is motorized data and also non-motorized data. So this we give them a separate identity so that it is not going to get into their personal identity as such, but it has a different identity by per se. So where they are moving, what is the way they are moving, and where actually they have been I mean traveling. So it's very well known. So travel zones are being demarcated in terms of this. So yeah, so this is how it is done. I will not get into all of these things. Probably you can look at some of those publications so that you understand it much better. So this is the raw video. This is the detected pedestrians, detected traffic. Then you have a gallery. So this is camera 1. So it will look at in a camera 1, it says, okay, this person is found in this particular zone. And it also identifies in different regions where this particular person is moving. So with that, we look at person tracking in terms of image pair comparison, which is going to give where the trip has happened and from which point to which point this particular person has moved. So yeah, we use something like bike track, which is a vehicle tracking algorithm. I'll just show you one video, which actually yes. So this is how the tracking happens. So you can see, and there's a person. This is traffic police that is there in between. Then there are cars moving. So each of these are ID'd. So wherever they are actually moving in, and whichever directions they are actually moving in, we are giving them that this how the vehicles are moving. This how people are moving, this how they are interacting, and at a particular point of time we know how many number of cars, how many number of motorized vehicles are there, how many number of non-motorized vehicles are there. The main aspect of this is developing an air pollution or a climate controlled model in order to see if this can be easily controlled in a particular region or not. So these are some case studies of what we have done so far in terms of looking at urban growth, urbanization, and climate-induced effects. So having said this, IIT Kharagpur is trying to develop uh, something in terms of how we can connect spatial and temporal data. So we are trying to look at how different solutions can be brought in. So very big flagship projects that have been put in. One of those is Urban Observatory. Urban Observatory is one of the new dimensions that have been taken up. If you see UN charter also, urban observatory is one of those major aspects that is considered in today's context, where we see how the urban growth is happening and how different aspects of this is connected, whether it is visualization or looking at indicators or using sensor data to look at various quality of life are being considered in urban observatory. So we submitted a draft report in terms of how the legal and policy perspective should be there when if it's transport, what should be there, and how do we develop an urban observatory to Government of India through British High Commission. So this has been developed through the funding of British High Commission. So it was submitted to Government of India for the further activities. So we have, I mean, there are some of these reports have actually come through today in terms of some of the implementation that is going on. And you can see that we developed one of these web spaces that's called SWAT in terms of how this particular data that we have developed it will be put into the public domain so that people, everyone sitting at every point, space can utilize this. This is one of those smart campus that we developed, which is actually implementing all of these aspects in this particular whatever I've shown is being regenerated here directly. So it is directly connected to the high performance computing. So any data that you are going to put is going to translate it here very quickly. Uh, yeah. So these are some of them. I would not. So this and we had a small this project in terms of converting IIT Kharagpur as a smart campus, wherein many of these things were set up in order to. And whatever I've shown is here is some part of this work that we have done in terms of the smart campus. So IoT sensors have been put up at every point, every place, and each of these sensors are monitoring different aspects. So when you look at this, this is what would be the final model that we want to develop. We have an wireless data that is coming in. We have an IoT gateway that we have set in. You can see this. There's an IoT gateway that is there. So now we are trying to develop the web application, the mobile applications, wherein all data can be easily sourced in, and some of the data is being generated through satellite data, and you have databases. I told you that all of this data are punched in terms of geographical connect, and then there is data that is fed in as attribute data. These data are then attached to the databases, and that is going to create the entire data model. With this data model, any kind of application that people want can be easily shown with all the data that is crunched in. So these are some of the communications that we have already done. So probably you can find out some of this. So I spoke about Bangalore. So that was some of those we pursued for a longer time. So we did write on Hyderabad, we did write on various other places across India. The way it is changing in very fastly and very quickly. So yeah, this is what I wanted to speak to all of you. And thank you very much. These are my collaborators who have been collaborating over a period of time. And yeah, so I welcome if there are any questions that you may have. I'd be happy to answer.
Thank you, sir. So participants, if you have any doubts, you can ask. Open to you. So any doubts, any clarifications? So you can ask. Bharat sir is available now. So if you have any, if you don't have any queries, or if you are not able to communicate through voice, or you can drop a chat so that sir will try to clarify your doubt. Any doubt? No, no, no. So, if you have any queries, you can ask contact mail to Bharat sir. So now I'll try to propose vote of thanks. So it is my privilege and honor to extend my vote of thanks to organizing committee for this organizing this kind of faculty development program. And first and foremost, I would like to express my deep gratitude to Bharat sir. Thank you, Dr. Bharat sir. Sir, thank you, sir, for your valuable information. And your information, most of the things we can relate in terms of you mentioned about the Bangalore city, how Bangalore city developed. So when we are very much near to the Bangalore city. So when we go to the Bangalore city, we can face whatever you mentioned. We can relate. So and there are so many things are there, sir. But actually, when I heard this kind of MDP, when I see this, when I heard what the work you're doing at your institute, so many things we can do. Go for there. It is like eye opening or opening new window for new domain of research instead of conventional building materials, conventional soil mechanics, conventional environmental, instead of conventional, you see whatever the points you mentioned in your work, those points are very much attractive and thought provoking, and we can relate. And in that, mostly when I'm traveling from one place to other place, I used to see this ribbon development, as you mentioned. So this ribbon development, I used to think like, why people are not able to control this kind of ribbon development? Because this ribbon development I heard in my diploma. I studied in town planning town planning subject. In that, I got this ribbon development concept. So that is what I can relate most of the things. So you explained this about ribbon development and all. So quantification of surface temperature and elevation maps, quantifying and creating elevated maps, horizontal maps, and person tracking, vehicle tracking, which is for most of the automated vehicles. So when I see this kind of presentation, we can't restrict ourselves to only civil domain. We can extend our arms to collaborate with the different domains so that this kind of outputs and in this, as you mentioned, smart campus at your IIT Kharagpur. So, sir, actually, this is we also in the same line because in our curriculum we added IoT sensor technology for our students. So we also going to become implement whatever the methods you followed at that institute in your institute. So you're grateful insight knowledge, and it is for me it is a new window to open think beyond whatever the domain you are working in it. So thanks for that enlightening talk, sir. So it gave me so much of problem statements in your. So why can't we think like this? So uh, so that is what my heartful thanks to you, sir, for your knowledge and expertise to give
Thank
it to us.
thank
So next, I would like to extend my sincere thanks to my VC Vice Chancellor Yuvraj sir and my management. to support organize this kind of program. And my team from head of the department, Deepankar Roy, and our organization team, I thank they made me to a part of this excellent program. So this is why actually I impressed. I mean, I inspired from whatever Bharat sir mentioned topics. So I'll try to work on that with collaborative efforts, sir. So if you accept.
Right, right.
I'll,
Definitely.
sir, and I'll try to extend my thanks to my supporting team and technical team. So those who without those people we can't able to organize this kind of FDP smoothly. So once thank you for all making this FDP this session more successful, and try to grab the thoughts that thought provoking things. So many valuable points are there, whatever the Bharat sir mentioned. So please work on that, and uh, we'll continue to do the inter-collaborative research in coming days, sir. So thank you, sir.
Thank you. Thank you very much. Thank you.
So, thank you so much, sir, for giving your valuable time.
నువ్వు ఫోన్ చేస్తున్నా ఆయనతో మాట్లాడుతున్నాను నేను.
దీనికి దానికి టచ్ ఉంది
దీంట్లో చదివే చెప్తున్నాడు. ఎందుకంటా ఏమన్నారు? ఎందుకంటే అర్జెంట్
ఎండెడ్ మ్యామ్